Welcome everyone to this week's HoloTube. We have Brian Swingle, and we're very happy to have him tell us about cosmology as a holographic wormhole and show us breathtaking images.
Yeah, thanks, Matthias. Thank you all for the invitation and for being here. And yeah, so today I'm going to talk about, in the spirit of this group, I'm going to talk about kind of an application of holography, or sort of unusual, what could be viewed as an unusual kind of quantum phase of matter, where somehow it encodes a cosmological universe inside that phase of matter. And so you could view this as kind of an application of holography to cosmology, or as a kind of interesting non-trivial quantum phase of matter, as I'll explain later on. The other thing that I'll say is that I spend most of my time nowadays making these AI-generated images. So on the right here is the universe is a hologram as made by Midjourney, which is one of these AI image generators. And I'll show more of these throughout the talk. I think it's really kind of amazing what they can do. And it's very fun and inspiring. So I encourage you to give it a shot. And let me just also acknowledge, my funding. So from Qubit, it's actually ending this year, but we're also very happy to have support from these various government agencies.
Well, I don't know.
And yeah, let me get started. So the background here, which I think you all know very well, is this very fruitful interchange between quantum gravity, primarily AdS CFT, and quantum matter. The idea, in one direction at least, that AdS CFT, or the kinds of large N strongly coupled CFTs that occur that describe simple models of quantum gravity, could be viewed as interesting kinds of quantum matter, quantum field theories. And if we sort of find the right kind of quantum gravity setup, maybe we can learn interesting things about difficult problems in quantum matter. And sort of the other way, maybe we can, using the sort of understood basic rules of quantum matter and quantum information, maybe we can learn something about the way quantum gravity works. And this has been, from my view, a very, very fruitful exchange. And all kinds of wonderful connections have arisen from it. But one very significant problem that remains is to have a more realistic kind of quantum gravity, meaning something more like flat space, or maybe even like a cosmology as we see in our universe, with an accelerating, expanding FLRW kind of space-time. And so this talk is going to be about that. Just before I go on, I'll mention that this picture on the left here is what you get from a unification of tensor networks in quantum space-time. So it sort of seems to know about the cylinder of AdS CFT, rather surprisingly. And I guess this is the tensor network here on the time slice. So that's nice. And on the right-hand side is an entangled state of electrons. And I think it's pretty clear it knows about Penrose diagrams. So you can see here, I guess, the electrons forming this thermofield double state. So, the AI is on board with the importance of this connection, and I think it's smart to think so. So yeah, in this talk, I want to talk about cosmology and, like a particular scenario. We, of course, don't know if this is the right scenario. It probably needs some modification at least. But the idea of this scenario is that we want some kind of totally non-perturbative microscopic theory, so something like the CFT. And we want this set up to generate a preferred state of the cosmological universe. That's the two ingredients we're looking for. This is based on a bunch of papers. My current collaborators include Stefano Antonini, who's my student at University of Maryland, Petar Simidzija, who's Mark Van Raamsdonk's student, along with Chris Waddell. And so Mark is kind of my senior collaborator here. And then Stefano, Peter, and Chris are the very excellent PhD students doing most of the work. And yeah, we recently had this series of 3 papers kind of laying out the current version of this idea and arguing that accelerated expansion is possible to achieve in this framework. And then we have some more work in progress that's coming soon. There's also some prior works. I think this idea kind of goes back in some form to a paper I wrote with Mark and others from UBC, I guess in 2018. And then Mark and I as well, we've expanded on that idea quite a bit, as I'll discuss later on. And there's also some related ideas. This paper here is about kind of analytic attenuations of a different sort and trying to compute observables in cosmological spacetimes using AdS. There are also ideas, for example, this paper of Boyle, Finn, Turok, talking about imposing novel kinds of like CPT symmetries to give a different version of the cosmological story. And there's also, as I'll highlight, connections to islands that have come up in the black hole story. So there's a rich history, but these three papers here are kind of the current state of the art, I would say, in our thinking. And yeah, I just want to highlight again Stefano, Peter, and Chris as the students doing a lot of the work here. And so the basic idea is we're going to ask about whether we can have a cosmology which is realistic, but with a negative cosmological constant. And the starting point is to say something like data shows that we have a period currently of accelerating expansion. I think that's very clear from like supernova data, for example, that definitely the universe is expanding and it's accelerating. Now, one very parsimonious explanation for that is to just posit that there's a positive cosmological constant. But this is not essential. In fact, you can also get the same kind of acceleration with a negative cosmological constant and some time-dependent scalar field. And I'll describe in detail how that works later on. And we don't at present include any kind of time-dependent scalar in our minimal model of cosmology, lambda CDM, at least not on the kind of background level. But on the other hand, these such scalars, they respect all the same symmetries as this FRW universe. So from sort of an effective theory point of view, it would be strange if they didn't occur. And then another motivation for thinking about negative cosmological constant is that it's much better understood theoretically and offers, again, the prospect of some sort of holographic description. Right? Maybe there's a way to do holography with positive cosmological constant. I'm not saying it's impossible. I'm just saying that we understand holography much better in the negative case. And so if that can also give us a realistic cosmology, it's worth thinking through the physics of that scenario. So that's kind of a starting point of our study. But I want to emphasize that just because we have a negative cosmological constant, it doesn't mean that the setup is sort of trivial or straightforward. In particular, in the cosmological spacetime, there is no asymptotically AdS region. So it's not like this is embedded in some AdS in a direct or simple way. The anti-de Sitter space will come up in a sort of dual picture, as we'll see. And so it's still challenging to understand, what is the physics of these situations. So to kind of give you a flavor of how it's going to go, let me show you a very simple example. This is an effective field theory example. So I'm not claiming this corresponds to any precise CFT setup, but it's just effective field theory. You have at the top here, Friedmann equation, the two Friedmann equations here, for a situation where you have a flat FRW universe filled with radiation and negative cosmological constant. And I've absorbed some G newtons and 8 pi's into the definition of the mass density, of the energy density. So this is a sort of reduced equation. And it's not too hard to actually solve this equation analytically, and you obtain the following scale factor. So it's a function of the time t, and has this kind of square root of cosine characteristic form. And so in particular, this is a big bang, big crunch cosmology. It starts small, it grows to some midpoint where it has maximum size, and it recollapses in a time symmetric way. Okay. And now where does the AdS come in? Well, if you go to this time symmetric point and analytically continue the coordinates, so you make the cosmological time, turn it into a space coordinate, and then take another one of the space coordinates and turn it into a time coordinate, what you can see is that instead of this cosine, you get a hyperbolic cosine. And so you actually get an anti-de Sitter space asymptotically as you go out. However, there's actually two sides to this, just like there is a big bang and a big crunch. And so the doubly analytically continued situation actually describes a Lorentzian traversable wormhole between two asymptotically AdS boundaries. Okay. And I want to emphasize there's no accelerated expansion yet. This is just this simple effective theory. But the idea would be that if this has a microscopic CFT description, it could be described in terms of two coupled holographic CFTs, say one associated with this back boundary and one associated with the front boundary, which are coupled in some way. That's what makes the wormhole traversable. And then that construction of two coupled holographic CFTs would somehow secretly encode also this cosmological spacetime. Okay. So that construction is already interesting to understand if it's possible and to understand the physics of it. What we're going to further ask is that can we get accelerated expansion? And as we'll see later in the talk, the answer will be yes. Okay, but that's the kind of starting point. So at this point, any questions about the kind of background, motivation, the main idea, anything like that? Okay. So here's another one. This is cosmology from the vacuum. I guess this is like, I don't know, it's like a vacuum pump with planets, and it's quite stunning. I'm not sure exactly what it is, but it's very fun. I'm going to describe now the kind of microscopic setup to flesh out the little story I told you just now, and describe kind of the general framework that we're thinking about. And then I'll go on and talk about accelerated expansion. So let's first set up the framework. As I sort of hinted at before, we're going to have two copies of some three-dimensional holographic CFT. So that's this red line here and this other red line here. I'm suppressing two of the coordinates. So I'm just showing as a line, but you can imagine it's extended in two more directions. And its translation invariant along this red line. And then we're also going to have a four-dimensional quantum field theory. Maybe it's a CFT, it doesn't have to be holographic, doesn't have to necessarily be conformal, but let's say it's just some conformal field theory that's going to live on the same space as the three-dimensional theories, but with an extra interval. So this is the interval. So the green part here is the 4D theory. And the idea is that this 4D theory is going to have some small number of degrees of freedom. So the central charge or some measure of the degrees of freedom of the 4D theory, much less than the 3D one. But it couples these two kind of large degree of freedom three-dimensional theories. And in the right situation, we want to argue that this coupling can produce effectively a connection between these two holographic endpoints. Okay, and that connection is going to manifest as the wormhole or as the cosmology, depending on how you view it. So that's the basic starting point. And the idea of the duality I referenced before is that there are two ways of viewing this construction. We can think of this picture so far as a purely Euclidean construction. So there's no time. It's just everything's Euclidean. But then we can slice this Euclidean object, this Euclidean path integral, say, in two different ways to get two different interpretations of the same Euclidean theory. If we slice it this way, along the 4D theory without cutting through any of the 3D degrees of freedom, then there just is no 3D stuff in the theory at all. This describes really a state where you have some kind of boundary condition in past imaginary time, and then some period of imaginary time evolution given by this green block, and then a quantum state on this surface. So this path integral is computing the inner product of this quantum state with itself, the norm. And so this slicing would really prepare a state of just the 4D theory at this time symmetric point, or at this point of reflection symmetry between the top and the bottom. So this is like some excited state of the 4D quantum field theory. Excited because it starts at some finite time in the Euclidean past and evolves for just a little bit here. So you're not going to push all the way to the ground state. You're just going to have some excited state of this theory. Okay. Now, the other way of slicing is to slice in a way that cuts through the three-dimensional degrees of freedom. This can also be done in a reflection symmetric way. And what this would describe is now not an excited state, but a ground state, because we have infinite amount of imaginary time. but it's a ground state of a theory that's got 3-dimensional degrees of freedom coupled to this 4-dimensional bulk here. And I say bulk, I don't mean holographic bulk. I just mean some 4-dimensional quantum field theory coupled to 2 3-dimensional field theories at its boundary. And so it's slicing 1 or picture 1, which is going to describe the cosmology, and slicing 2, which is going to describe the Lorentzian wormhole. And the idea of this duality is that these are 2 different ways of looking at the same physics. So we have the same Euclidean theory. From one point of view, it describes some kind of cosmological universe. From another point of view, it describes a ground state of some kind of complicated, sandwiched quantum matter theory. Okay. And what we want to imagine is that this coupling, this green coupling between the 3-dimensional theories, that this coupling is going to cause these theories to become strongly correlated with each other in the infrared. So there'll be some kind of RG flow. It could be a long RG flow. That's okay. That may be even what you need. But ultimately, the effect of this coupling is to correlate the top dark red 3D theory with the bottom dark red 3D theory via this emergent holographic wormhole, in this case, a Euclidean wormhole that connects them. Okay. So, of course, these Euclidean wormholes that connect different boundaries are subject of much discussion nowadays in quantum gravity. What do they mean? Are they allowed solutions? In particular, like, don't they present a factorization puzzle where we would think these 2 different 3-dimensional theories are independent of each other, really? Here, it's no problem because we have a very explicit coupling between the 2 theories. And so therefore, it's perfectly reasonable to imagine that there could be some sort of connected solutions that contribute to the gravitational path integral. Okay. And so if you have this kind of connection between the 2 3-dimensional theories, then we would interpret this from the boundary point of view as saying that the 4D theory has caused RG flow, which has led to a gapped or mostly gapped infrared description of these 2 3D theories. So they kind of get glued together. Maybe there's a few low energy degrees of freedom left, maybe some Goldstone modes, for example, but most of the degrees of freedom are gapped out. And this describes some kind of coupled phase of these 2 previously separate 3D theories. And then again, we have these 2 different ways of slicing this. If we slice it in the first way, which I've coded as blue, then we have essentially this cosmological picture that we get from taking this wormhole and cutting it this way here, and then asking what is the analytic continuation of that? Well, you get this excited state of the 4D theory here, and you get some kind of cosmology from this region over there. And similarly, if you slice the other way, so cut this way through the cylinder, the coupled theory, then what you get instead is this traversable wormhole that describes the coupled combination of these 2 3D theories coupled via the 4D theory. Okay, and this is like a ground state problem. So one of our papers is titled, Cosmology from the Vacuum. That was the title of this section. And so you're seeing here how this vacuum state of this particular kind of coupled theory secretly by this dual analytic continuation describes actually a cosmology. Let me just mention one special case, which is what we actually studied first. This is what was in the old 2018 paper with Mark and friends. That was the situation where this 4D theory, the green thing here, is itself holographic. And then you could kind of like fill in the interior of this sort of topological cylinder with some spacetime, some AdS5 spacetime, say, or some more general solution. And in that way of thinking, this sort of light red region here was like an end of the world brane that connected these 2 boundary conditions on your 4-dimensional holographic theory. So it was like a setup that was describing the situation where you have a holographic 4D theory terminated by 2 kind of holographic compatible boundary conditions here and here. And the result was this 5-dimensional gravitational space-time cut off by an end-of-the-world brane, which described the effect of the boundary condition in the bulk. From the bulk gravity point of view, this brane was actually behind the horizon of the black hole. So there was a precise sense in which it was very hard to extract physics about that situation from the point of view of the AdS4. I mean, from the point of view of the 4-dimensional theory. So really the picture was, this is not just any old excited state with the 4D theory, it's some very complicated micro state of a black hole that secretly in this behind the horizon region encodes a cosmological evolution on the end of the world brane. And so this paper was called Black Hole Microstate Cosmology, and it was this basic idea. Now, there are some technical difficulties in that paper in terms of getting everything to work at the level of effective theory. And one of my contributions of my student and myself was to modify the setup a little bit by adding charge so that you could actually push this brane very far away from the black hole horizon and reach a situation where you have something called gravity localization, which just means that gravity on the brane would behave more or less like 4D gravity, not 5D gravity, which obviously is a condition one needs to match data in the universe since gravity looks 4-dimensional. But so that's like kind of another direction one can pursue, but I won't talk more about that here. So let me just summarize the setup. We have what we call this Euclidean sandwich theory at the top. And there's two different ways of slicing it. So the solid black arrows correspond to different ways of slicing. In the one case, we get this excited state of the purely 4D theory. In the other way of slicing, we get a ground state of the coupled 3D, 4D, 3D theory. And then if we do holography to this situation, the sandwich theory from the quantum field theory point of view should turn into this Euclidean wormhole. And then there are now two ways of slicing that wormhole to make a real-time space. In one way, you have this cosmology picture, so that's dual to the excited state. And in the other way, you have this AdS4, asymptotically AdS4 traversable wormhole. Okay. So this is just kind of putting that, if you like, that example of negative cosmological constant plus radiation, it's kind of putting it into a bigger framework where it's one example of this class of Big Bang, Big Crunch cosmologies, which potentially via this slicing duality could be related to some well-defined coupled field theory system. Okay, this is just one more kind of just trying to drive home the basic point here, but now from an effective field theory point of view, from the point of view of effective field theory on this cosmology, you have just the 4D theory. It's some excited state of that 4D theory. That state is maybe dual or in some sense entangled to this state of the cosmology. This is very similar to the recent discussions of islands in cosmology, if you're familiar with those papers. Somehow this cosmology has some degrees of freedom in it that are entangled in some sense with the degrees of freedom here, but it's really like describing a certain kind of state of this theory using the cosmology. And then equivalently, we have in the other way of slicing this wormhole where you have the two ends, the two 3D theories, the bulk 4D theory, and then the wormhole that emerges to describe the coupled system, thanks to the fact that this 4D theory triggers a relevant RG flow that results in some correlated phase. Okay. And so just to emphasize, we do have what we want, what I set out to have at the start, which is a special state for cosmology. That's because this Euclidean path integral, which is what we're talking about ultimately, does define a natural state at the turning point, at the point where the universe is either as big as it can be in the cosmology picture or as small as it can be in the wormhole picture. then we have a special state that's defined there via the path integral. And we could then hope to understand earlier times by evolving, say, forward or backwards away from this turning point. And importantly, like, this is far away from the singularity, so we don't seem to need to know anything about the singularity, particularly to describe physics of, our universe necessarily. There are some interesting kind of features. There's all these famous puzzles in cosmology. Why is the universe flat? Why is there this cosmic coincidence where the cosmological constant and matter radiation are like close to being equal right now? How do we have these long-range correlations? And some of these puzzles have new potential explanations in this framework. So for example, we kind of just built flatness in as a symmetry. You still need to worry about fluctuations, of course, but at least the background is flat. The cosmic coincidence problem is maybe not as much of a problem because it's very natural for these two things to balance at the turning point. That's actually one of the simple conditions from the Friedmann equation. So as long as we are sort of close to, but not quite at the turning point yet in terms of where we are in the universe, then it might be natural for these two things to be relatively close to each other. Similarly, this horizon problem is also confusing. Like, how can you have these long-range correlations? But in our situation, because there's one point of view where the theory describes a ground state, then you could expect long-range correlations with such a ground state, right? If you have a ground state with some massless degree of freedom, you will have power law decaying correlations. So the fact that you have this ground state version or slicing of the theory suggests that you can have long-range correlations. Now, I'm not claiming that these match data yet. That's a more complicated question, but at least it's not wild to imagine that you could have correlations between very long distances in this theory. So somehow this special state could build these in some way. It might still be the case that there's perhaps some kind of inflationary point of view on this. We don't know. So it could be just an alternative to inflation, or it could be like another way of describing the effect of inflation. It's not really clear at this point. But yeah, that's a question that we're still thinking about. And yeah, just drive home again, what corollaries am I talking about? In particular, these ones that are on the time symmetric slice for both different slicings, so both ways of defining time, correlators on that special codimension 2 surface are exactly equal in the cosmology and in the vacuum, right? So any such correlators, we know exactly what they are, and they're equal. And so then from this information, you can try to, describe more generally what is happening outside the special surface by evolving away from it in some way. Okay. So that's the framework that we're proposing. And yeah, at this point, we're not talking about acceleration yet. We're just saying this is a way of thinking about Big Bang, Big Crunch cosmologies, in particular time symmetric at the level of the background, Big Bang, Big Crunch cosmologies, from the point of view of holography. So there may be a holographic dual of such situations which proceeds via this slicing duality. Of course, I didn't show you that there's any particular microscopic theory that achieves this. This is just all the level effective theory. But at least you have this potential framework, and you can ask if there are interesting examples within this class. Okay. So now I'm going to go on and talk about acceleration. But of course, if there's any questions about the previous stuff, please feel free to ask. But if not, I will go on. So let's talk about acceleration now. This is actually on the right here. You see for sort of a Halloween project, I made quantum space-time tarot cards. And this one on the right, these are two different versions of Accelerate, the Expanding Universe tarot card. So I made a whole bunch of these, and this is just an example here. But it's, again, pretty amazing, like the planets, and I don't know, maybe they're just supernovas or something. It's pretty cool. So let's talk now about, continue with this discussion of effective theory and ask whether we can have solutions where we have not just this Big Bang, Big Crunch structure, but actually acceleration, because that's what we really need to have to describe the universe that we see. So acceleration is definitely happening. I'd say it's a very robust conclusion of the supernova data, which doesn't mean it's necessarily a positive cosmological constant, just that the acceleration has happened. Okay. And so let's explain a little bit more to start out how this slicing duality works from the point of view of the equations of motion. Okay, so you have these two different metrics, the cosmology metric on the left and the wormhole metric on the right. And we're going to ask kind of how these metrics are determined given the dynamics of the system. And in particular, as should be clear from this equation, we need to incorporate now a scalar field here called var phi, curly phi. Here in the cosmology picture, dot means time derivative, and in the wormhole picture, the prime means space derivative kind of along the wormhole, right? And there are these basically two different versions of the Friedmann equation and the scalar equation of motion, depending on which picture you're in. They're all determined by the potential, but the potential enters in a different way. So whereas it has the kind of usual interpretation in cosmology picture as giving a force, for the wormhole picture, because it's a space derivative, it turns out that it's more like the negative of the potential, which is kind of playing the role of potential. So there's a sense in which potential gets kind of inverted in this Euclidean calculation because this is a space derivative, right? And so again, why do we need scalars? Well, matter and radiation will not give us accelerated expansion, so we have to have a scalar field in the game as well. And essentially what we would like to do is somehow arrange for the scalar field to experience a portion of its trajectory, which is potential energy dominated. And in such a situation, you would then expect accelerated expansion. So as long as we can make the region where the scalar lives have a positive potential and make it live there for a while, maybe some kind of slow roll condition, then you could have accelerated expansion from that effectively positive energy density, even though there's another extremum somewhere in the parameter space where you have this negative AdS solution, negative CC AdS solution. So here's a kind of explaining how that works. And in particular, it's making the point that you might actually think that not only is acceleration possible, it could actually be, in a certain sense, generic. The reason is as follows. Let's look at the right panel first. So this is the potential of the scalar field versus the field value. This is some fairly generic potential. What we're imagining, though, is that the scalar field corresponds to a relevant perturbation. That goes back to the earlier point about the 4D theory triggering a relevant RG flow in the 3D theory. So we're going to imagine that 3D theory. This is some scalar field dual to an operator in that 3D theory that's relevant. And so what we're doing is we're sort of triggering an RG flow via this 4D coupling. And from the cosmological point of view, if we start from the turning point, the field will have some value. Let's call it this dot here, where the time derivative of the field as well as the time derivative of the scale factor are 0. So that's the condition for a time symmetric turning point. If you have that condition, you'll have a time symmetric universe. And if we start from that turning point and imagine going backwards in time, what happens? Well, because of the Hubble friction and because we're going backwards in time, effectively this scalar field is anti-damped, right? Because in the forward direction, it would be damped from the Hubble friction. So when you go backwards in time, it's anti-damped. So if we evolve the equations from the time symmetric point back towards the Big Bang, what the scalar field will do is it'll start accelerating, it'll start moving down this potential, it'll gain speed, then it'll start going up. But because it's anti-damped, it can actually reach a higher value of the potential than originally. And so it can reach some here, somewhere up here. And in principle, in this region where the potential is positive, if it can reach this region before the Big Bang happens, and in some situation where you have something like slow roll, or at least the potential energy is dominating, then in this region up here, you could get accelerated expansion. So then from the point of view of starting at the Big Bang, it would be you start the Big Bang somewhere else, you come down, you have this region here of accelerated expansion, then you keep evolving, eventually you start decelerating, you have your Hubble friction, which slows you down, and you come to rest at this point. And it's at that point then that you either do the time symmetric thing, or if you like, you can analytically continue, go to the wormhole picture, and now we flip the potential and you kind of slide down the potential to this AdS boundary here, where the potential is now negative, and there is an asymptotically AdS solution. Right. So again, the big picture here is that we have this fairly generic potential, and just from the fact that we have expect some relevant perturbation to make the story work, it's sort of plausible from the Hubble friction that you could start at this time symmetric point, kind of evolve backwards and reach a place where at least potentially you could be potential energy dominated and therefore have accelerated expansion. So maybe fairly generically within this class of theories, you would actually not just be compatible with accelerated expansion, but actually expect it. Okay. Now, here is a demonstration of that fact. So this is a potential that I just cooked up. It's not meant to be especially physical. It's just a symmetric potential. In fact, symmetry is also not important, but because it just moves in one side of the potential. But let's just say we have some symmetric potential here. We've normalized things so that the cosmological constant, or we extracted all the units. So the potential is just -1 at the phi equals 0 extremum. So phi equals 0 is the AdS solution. We want to reach some place where the potential is positive to have accelerated expansion. And so we have a mass term here, which we're going to control. We're going to set the mass to be right at the BF bound. And then we're going to have this other potential with one parameter G. And we'll just dial this potential parameter G as well as the initial condition phi naught and ask whether we can ever get accelerated expansion. So here's a plot of a double dot. I've zoomed in on a moment in time. The Big Bang is just a little bit further along over here. And then the time symmetric point is at time equals 0. So it's out this way somewhere. And there's this little tiny blip here, close to the Big Bang, or relatively close to the Big Bang, where you have a little period of accelerated expansion where a double dot is greater than 0. Okay. So I'm not thinking this is realistic or anything else, but just it does occur. I didn't like fine tune this potential in any real way. It doesn't happen if you just keep the phi to the 4th term, as far as we can tell, at least as long as you obey the BF bound. But if you consider a slightly more general kind of potential, then it seems to be possible. And maybe more to the point, it's actually codimension 0 in parameter space. So here I'm now scanning phi naught, the initial parameter, the initial condition of the scalar field, and this parameter G. And everywhere where there's like a grid here that I've suppressed, and everywhere you see red, there is at least a little part of the evolution which is accelerated. Okay. So what this means is that everywhere inside this red blob of initial values and potential parameters for a particular mass of -9/4, that's the BF bound again. Everywhere inside here, there's at least a little bit of accelerated expansion in the evolution. So the main point of this slide is that this is codimension 0 in parameter space. It's not like I need to fine tune G and phi naught. There's a codimension 0 region where I have acceleration. Again, doesn't mean it's like a lot of acceleration or anything like that, but it's at least codimension 0. So you could call it generic. Doesn't mean it's prevalent or widespread or common, but it's at least formally an open set in parameter space. In fact, you can also test, I only showed you here G infinite, we can also vary M squared. In that case, you see that as a function of M squared, here A is the same as before. Here B, M squared is -2. Now it's minus 1.75 and then minus 1.5. So I'm decreasing it from A, B, C, D. You can see for masses pretty close to the BF bound, I have a sort of significant region in parameter space. But as I increase the mass squared, as I make the operator less relevant, I quickly lose that parameter space. So here it's shrunk quite a bit. And by the time I get to minus 1.5, it's almost non-existent. And then it quickly goes away, at least as far as we can tell. So the relevance of the operator is very important to making this work, as might be not surprising from the story I told. And this makes it clear as well, I guess, that it doesn't necessarily have to be a super common phenomenon. It can be relatively fragile in some sense, but at least, again, it's still some open set in parameter space, including the mass squared. Okay. So I hope I convinced you that not only is acceleration possible, it's in some sense even generic. But okay, fine, the real current effective theory of the universe, lambda CDM, or the consensus model, is very fine-tuned. It has this very small cosmological constant that's positive. So let's now allow ourselves more fine-tuning, sort of a comparable amount of fine-tuning. Let's make the potential to be some very special thing. And let's ask how much of cosmic history we can reproduce within this framework. So we're going to consider a potential that looks like this. The detailed form is not crucial. If you want to know, it's some error functions in Gaussians with some parameters. It's just a convenient parameterization of potential that starts at -1 or at some negative value and then has a kind of drop into some valley and then goes up again and has a kind of quasi-flat region. Again, it doesn't need to be exactly flat, but the basic idea would be that you want to start somewhere here, just as we said in that previous cartoon. You want to start somewhere here in the cosmology picture. As you evolve back in time, you kind of fall down this pit, then go up again, and you want to tune things so that you end up at the top of the pit on the right side in this flat positive potential region with almost no kinetic energy. So you kind of start yourself at just the right place so that you drop down, the anti-damping pushes you back up, and then you end up at this plateau with almost no kinetic energy. And in that case, you'll have a potential energy dominated solution, and you can get accelerated expansion for an extended period of time. Okay, so it's really like you just want to kind of tune the shape of the potential, tune the initial condition so that you can fall down, come back up from the anti-damping, and just barely reach the top here with almost no motion. Now we can do that. So this is a plot showing the kinetic and potential energy of our scalar. We also include radiation and matter contributions. And then in purple is the scale factor. This dashed black line is where we are at present. And back here is the Big Bang. And then the 0 here is the time symmetric point. So you can see we're still like, we're very much in the middle of the evolution on this scale. And only in the fairly distant future will we, reach a point where we see the turnaround. So right now, the turnaround is kind of far away from us. And the point of this is just to show that we can find a solution, a full solution, by tuning that potential where, as I'll show in the next slide, we perfectly reproduce the scale factor of lambda CDM, or essentially perfectly, over all this range of times, from not quite the Big Bang, but shortly thereafter, to up, more or less up to the point where the scalar kinetic energy starts to dominate, and you have this kind of slowing down and turnaround point. Okay, so just the details are not important, just that we have this solution. This is a picture of in gold here is the actual lambda CDM scale factor based on the Planck 2018 data. So this is the actual model, the consensus model of lambda CDM based on the 2018 Planck data. The blue is the field theory, the effective field theory model that I was just discussing with that funny looking potential, where we've tuned things in such a way that we reproduce the scale factor over a very wide range of times. So again, at very, very early time, maybe you can see here, the kinetic energy is blowing up. So at very, very early time, we don't necessarily agree with lambda CDM, but that's a different story. Maybe inflation happens, maybe something else happens, we're not sure. And then at sufficiently late time, you will eventually turn around. But over this very wide range of cosmological times, you just reproduce the scale factor. Here's just to give you a sense of what we actually did. We can actually fit, for example, supernova data with this. It's something that you can do. These two different, if you look first at this plot here, this is the luminosity distance versus redshift Z. These are just supernova data. These different black dots are measurements from supernova. You can see these direct measurements of the scale factor essentially exist from about Z equals 0, more or less, up to about Z equals 2, or a little bit less. So it's relatively recently that this data comes from. And these two different red and green curves here, the red curve is the Planck 2018 fit. The green curve is just supernova. And the fact that these two differ is like a manifestation of the Hubble tension. So this is like one version of that here. And we can fit either of these data sets, but in particular, we can fit the supernova data. And we're not even showing the blue and gold curves, but they just lie exactly on top of the corresponding lambda CDM curves. So in other words, we can just perfectly reproduce what those models give for this range of scale factors of redshifts. Okay. So, maybe, one might hope, for example, that some version of this model could help explain the Hubble tension. Of course, we're not anywhere near there yet, but that's the kind of thing that you might, look for in this sort of setup. And just to give you a sense of the potential here, this little red region, which I've zoomed in here on the right, this is the whole potential. This little red region here is the part of the potential that you can directly reconstruct from the scale factor in this range of Z. Okay, so in this range of Z, the universe is more or less dominated by matter and by dark energy, or whatever this scalar field is in our case. And so from the Friedmann equation, you can just read off actually what the potential is, assuming you know the matter density. And that matter density is quite uncertain, in fact, so that it's actually, there's quite a degree of flexibility in how you do this fitting, but you can do a fit. And this part of the potential is essentially just determined directly from the scale factor data. So we assume the scale factor is known, we just sort of more or less read off the potential. And what I hope this makes clear is that, you're only probing a small region of the potential. So this theory definitely predicts that there should be a time evolving scalar field. Like that's a necessary condition for this framework to describe reality. But the region over which it varies in terms of the potential energy may not be that much, right? So, and in particular, we have a lot of freedom away from this directly known region to modify the potential to make it compatible, say, with this wormhole picture. Okay. But this will be kind of the part of the potential that's most directly constrained by direct measurements of the scale factor. And you can see there is, some variation of the potential as a function of time. So the scalar field is moving. And, one could hope with better and better data to actually see that this time dependent scalar model is a better fit, say, than lambda CDM. But in practice, as we showed, they're quite close. Okay, so that's the main story I wanted to tell you. Be relatively short today. The takeaway is that we're really encoding an entire cosmological history as a complicated, excited quantum state of some 4D field theory. This 4D theory doesn't have to be holographic necessarily, it doesn't have to be large N, could be some like more or less ordinary quantum field theory. And somehow we're encoding all of cosmology inside that theory, right? So it's using those degrees of freedom of that excited quantum field theory to secretly describe this very complicated setup. And I also told you about how we have, in the right situation, this kind of slicing picture, which can relate this complicated cosmology to a potentially much simpler vacuum description. And that vacuum description is nice because it gives, among other things, easier access to observables. It gives you a sense of, say, why, for example, you might have long-range correlations in space, something that we certainly would like to understand. Inflation provides one explanation, but there could be others. And so there's different possible, I'm not claiming we solved some problem, but there are new suggested possibilities. For example, coincidence, like I said, may not be so surprising once you have this turnaround. At the same time, well, let me also say, like, this encoding is very much in the spirit of, it was independent of, but in the spirit of the islands in cosmology story. And on the right here, you have a holographic island inside a black hole. So this is kind of the spirit of what we're going for. So it's somehow this cosmological universe, which is entangled or encoded with some bath. That was the language that the islands in cosmology folks used. Here we see that the bath is really just this, some kind of coarse-grained description of this 4D quantum field theory state. And the cosmology gives you a purification, so to speak, of that coarse-grained description. And then there's some microscopic, very complicated description where you have some particular precise quantum state. Okay, so I hope I convinced you that we have now this framework for Big Bang, Big Crunch cosmology, and this framework, at least at the level of effective theory, can actually incorporate accelerated expansion, or with enough tuning, even be made to essentially agree with some consensus model at the level of the background. But there are like a lot of questions still to go, and I think a lot of interesting questions, even from the point of view of sort of the quantum matter side of things. One in particular that I'll highlight is here, that this question of perturbations. So everything I talked about was about the background, but we'd really like to match the perturbations as well, of course. That's a crucial part of the puzzle. And we'd like to understand, like, do we need inflation, primordial inflation? Or can these models produce the right spectrum of perturbations even without that physics? That's kind of an interesting question in quantum matter, because it's like these two coupled 3D theories coupled by the 4D thing. And what these cosmological perturbations predict is that you should have some very maybe unusual pattern of correlations in the ground state picture. For example, the oscillations you see in CMB, that should be encoded somehow in the ground state of this theory. So that's an interesting kind of, what kind of phase of matter would do that? Another thing that's really important to understand is these wormholes, they need a lot of negative energy to stabilize them in the Lorentzian picture. And it's not clear whether that's really possible. In fact, Mark, Peter, and Alex May have a nice paper from, I guess, a year or two ago, where they show that you can get this large amount of negative energy in a holographic model, where you model the effective theory as a holographic theory, so sort of like a doubly holographic setup. And Mark and I have a forthcoming paper where we just look at just free Dirac fermions, massless fermions, and also argue that you can get large amounts of negative energy in some sense. It's not exactly what we need for this wormhole yet, but it's at least hinting that maybe this negative energy is not so difficult to obtain. The role of supersymmetry, I didn't talk about at all, but it's it's actually probably pretty important. The era of time is a sort of interesting conceptual question. And then, this question of, do we have anything to say about the Hubble tension? And also relatedly, would having the scalar field do anything else? For example, if I have this very flat region, that means that the mass of the field in that region is very light. So there should be some very light particles corresponding to fluctuations of that field, like a fifth force. Are these dark matter particles? Are they just, is it all ruled out because you would make too many of those, et cetera, et cetera. So there's lots of interesting kind of pheno questions about what the physics of these models would be. Again, once you start including perturbations. But that's the basic story. Thanks for listening, and happy to take any questions if you have them.
Yeah, thank you very much, Brian, for an inspiring talk, both content-wise and visually. Other questions?
Matthias, can I ask a question?
Of course.
Yeah,
sure,
please.
Navid.
Oh, hello, Brian.
Hello.
Thank you very much for the very nice talk. My question is related to one of the plots that you showed about the content of radiation and matter fields after this process of maybe not inflation. Oh, exactly this.
Yeah.
But then I would like to understand how to realize, for example, reheating in this framework, how this scalar field deposits its energy to the radiation and those things.
Yeah, good. I guess, I could say two things. So the first thing I can say is that, in like inflationary picture of reheating, it's something like the inflaton or something that's depositing its energy. And this field doesn't have to be that field. So this could be a field that's responsible for like the late time acceleration. Then we could imagine there's another field there's no real reason, I think, that they have to be the same. So it's possible that we should just not trust this solution in this region very early time, and that there's some other field that's coming in that's maybe doing something like inflation for us. And then you could have a fairly conventional story of reheating. But it's also possible that there's, that there is a way of doing reheating here. We really don't know yet. We just haven't thought about that. So yeah, I'd say it's essentially an open question. And in particular, this issue of whether like we need inflation as an extra thing to make the perturbations work right, or whether in some sense they can come out automatically.
And then could you please also say, how do you obtain this red plot here? This red curve here.
Yeah, this is just the matter contribution to the energy density. So we have these three parameters. We have like omega matter, omega radiation, and then the scalar field parameters. And we're simply fitting these. So like in the, let's see, I have the Friedman equation somewhere. Yeah. So this is a radiation term. This F over A to the 4. So we just also add I guess this is a slightly older version of these equations, but we also have a matter term here. So 1 over A cubed. And you have just some parameters that tell you what fraction of the energy density is radiation and matter at a given moment in time. And then we adjust those along with the parameters of the potential here to find a solution which gets very close to the lambda CDM scale factor.
Thank you. Yeah, got it. Thanks.
Thanks for the questions. Any more questions? I was wondering if for the universe to reproducing the history of the cosmological evolution, you would also need baryons. And did you think about baryogenesis and fulfilling Sakharov conditions in this setting?
Short answer is no, I did not. I would like to, or I think we would like to, but I did not yet.
It might give some more constraints on the model. I mean, I understand at the moment you're not trying to fit anything really to anything. Everything came out pretty generically, but maybe like including more important boundary conditions, like that there should be baryons.
Yeah, I mean, I think we definitely want to do this. I would say, like, things have evolved a lot, like as in 12 months ago, we did not have any of this like detailed matching. So we're now at the level of matching the background. And what I think we'd like to do, like to my mind, the two things that loom largest are the perturbations. So can we reproduce, say, the observed fluctuations in the CMB, in particular the peaks? That would be a very like 0th order thing that you'd want to be able to get right. And the centered story of that, involves a special initial condition here in early time created by inflation, a sort of zero velocity or phase matched initial condition. So it's not clear whether we have that or what you need to get that. And then, also the scalar field that we're predicting needs to be there. Does that lead to any undesirable effects? So in particular, the fact that it has this like very flat region here, say, means the mass is quite small in some units potentially. So that you would think might lead to a 5th force, or maybe the particles can be interpreted as dark matter particles. And this is something people have thought about before. So I think those, to my mind, are kind of the two most urgent phenomenological issues. But yeah, we want to understand eventually everything and whether we can make a completely well-defined model. And then ultimately, can we even find a CFT, some precise 3-dimensional superconformal field theory that does this? But, that's of course a bit further away.
Okay, great, thank you. Are there any more questions?
Matthias, I have one more question.
Sure.
Please.
Okay, good. Maybe back to one of your very earliest slides. You showed some assumption about the central charge of boundary theory and the theory in the bulk. C central charge of the 4-dimensional theory should be much smaller than the 2 boundary theory. Oh, exactly this one. Yeah. I didn't get the point about it. Why should we assume this condition?
I would say that the simplest, morally speaking, this is something like ensuring that gravity does not leak out of the 3D theory into the 4D theory. And maybe one precise version of this is here. So in this AdS 5, this sort of doubly holographic like model, the way we got this to work the best in this paper here with my student is to tune the tension of the end of the world brane to like near criticality. And in terms of boundary entropy, this is like increasing the boundary entropy by a lot. So like it's making it go to infinity as you turn the tension to criticality. So we're like kind of piling more and more degrees of freedom, more or less, on this boundary condition in some sense. And that could push the brane far away and also gave us localization of gravity. So it's somehow saying that like, it's like a condition for gravity to be localized, roughly speaking, that it doesn't kind of leak out. And you can see it pretty clearly in this brane setup. But more generally, I think we just don't expect that you need like a lot of degrees of freedom of this 4D theory.
Okay. Yeah, thanks.
Yeah.
So are there any more questions? If that is not the case, then thank you again, Brian.
Yeah, thanks for having me. Good to see you all.
We'll stop the recording here.